Let's take a few minutes to talk about thermodynamic versus kinetic control. And before I begin this discussion, I want to point out that this concept is not unique to additions to dienes. It can be applied in many different situations in organic chemistry. It's just that this semester, this is the first time we've seen an instance of thermodynamic versus kinetic control. So it's not unique to dienes. It's just, in this case, it is applicable, but it also has many other cases where it applies. Okay, so scientists have studied this reaction where we have butadiene plus HBr, and they found that it yields two different products. We call the red one the 1,2 adduct, and you can see how the H and the Br are basically added onto carbons that would be counted as 1,2 if you're counting along the carbon chain. The purple product is called the 1,4 adduct, and that's because we've added the H and the Br to carbons number 1 and 4 along this 4-carbon chain. So we call this the 1,4 adduct. So at 0 degrees, scientists observe that we get 71% of the 1,2 adduct and 29% of the 1,4 adduct. When we increase the temperature, we essentially reverse the ratio. We get 15% of the 1,2 adduct and 85% of the 1,4 adduct. And so what is going on here? Well, we can draw an energy diagram that looks something like this, and we start with the diene over here, and they both would go through the same cation intermediate. If we protonate the double bond, we add H to this alkene, we would end up with a cation that looks like this, and this is a resonance stabilized cation, so we could show that. So we have a couple of resonance structures here, and of course I have my Br minus in close proximity to that cation because it has just recently given up its hydrogen to protonate this carbon. So the Br is close to the cation right here. Now let's explore the two different options. We have the, let's see, the 1,2 adduct should be red. And the 1,4 should be purple. And so I drew the 1,2 adduct in the less stable position. You should be able to answer why it is less stable and why the 1,4 is more stable. Think about that for a few seconds. So the stability, really the only difference here is that we have an alkene on the end of a chain and we have an alkene in the middle of the chain. And of course this alkene has more substituents, so that becomes a more stable alkene. And that's why I drew the 1,4 adduct at a lower energy level than the 1,2. So the 1,4 is more stable, and that essentially is what defines our thermodynamic product. The thermodynamic product of any reaction will be the one that is the most stable product. All right, so we evaluate the temperature differences here, and at cold temperatures we find that we get more of the 1,2 adduct, and we get less of the thermodynamic product. And so this would be the kinetic product. Basically because we get more of it. We get more of it at lower temperatures. When there's high temperatures, basically the reaction is more easily reversible. It can go back and forth between products and reactants, and eventually it reaches equilibrium. We would expect the more stable product to form in the highest amounts, and that's what we see at the higher temperatures. Again, the higher temperatures allow the products to revert back to the intermediate here, and eventually we'd reach an equilibrium where the more stable product is favored. So we know that the thermodynamic product forms more at higher temperatures. So let's continue with my pathways here. So there's my kinetic product. That is the quicker forming product. You see that the EA here is going to be less than what I get with the thermodynamic product. So it takes more energy to form the thermodynamic product, but eventually, as we said, we get the most stable product. And so we need the extra heat energy here so that the reaction can go backwards. So basically what we're talking about is that the 1,2 adduct could potentially lose the bromine, driving us back up this pathway to the intermediate. And that intermediate can undergo resonance between the more stable cation and the less stable cation, but also forming that more stable alkene. And then if eventually we get enough of that, the bromine adds to it, that's what produces our 1,4 adduct. So to recap, at low temperatures, we get the faster forming product. We get less of the more stable product. At higher temperatures, we have the ability to take the 1,2 adduct back up to the intermediate, do some resonance, and eventually add the bromine to the outside carbon, allowing us to then follow this purple pathway, forming the more stable product. So that happens at higher temperatures because we have more equilibrium happening, more reversibility happening. Okay, so why is the red pathway quicker and it forms the less stable alkene product? Why is that the kinetic product? Well, scientists propose a proximity effect, and you can see that if I erase my red line here. You can see that once we form this cation, the bromine's in pretty close proximity to the cation, and it's very easy for it to add to that cation, forming the red product. And so that's where we get the faster forming kinetic product from. If that cation undergoes resonance to form this cation on the end of the chain, the bromine probably has to float around in solution for a few milliseconds longer in order to get into close proximity to do the nucleophilic attack on this cation. And so that takes just a little longer. That might account for the higher activation energy here that we see with the purple pathway versus the red pathway. And so it's called the proximity effect. And that's where the bromide anion is perfectly placed to react with this cation, which leads to the less stable alkene. However, it is the faster forming alkene. All right, so let's look at another example just to practice this concept. So here is a potential reaction that we could talk about. So the first thing we'd want to do is evaluate the temperature. This is lower temperature, so most likely we're looking for a kinetic product that would form via the proximity effect. Probably wouldn't use any resonance. So let's look at forming the intermediate. And I have two cations that I could form. I could form a cation here or here. And the first thing I want to do is decide which of those would be favored. And I think it's going to be the bottom one because we can get some resonance stability there. So let's put a circle around there. You can see how we could get resonance stability. And of course, we've got our bromine here as well. And so again, low temperatures tell us we're going to form the kinetic product. We're not going to undergo this resonance. So we should immediately attack that newly formed cation before it undergoes resonance. To produce this product here. And so that's going to be the slightly less stable alkene. This is the kinetic product. Let's look at what we'd form from the other alkene, just for kicks. So here we get the more stable alkene. This is a tetrasubstituted. This would be the thermodynamic product. And so in this case, we have the minor product. And we have the major product. And that's how we might answer this question. So the kinetic product is the major product in this case because of the lower temperatures. Another thought experiment you could do is if we just change the temperature here to 40 or 50 degrees C, how does the outcome change? And you can think about that.